did repeat or something like that, and then you just you can also use for him. You drag in this, drag it in to now the subsystem above. Okay. So now, I mean, so now the fun part is if I wanted to model a system here that had lots of masses, it gets to be really easy. All I have to do is make, let me just give myself a little break here. So in this case, I'm going to model 3 masses. I don't know, or I mean, even I think the problem I wanted to do is okay, so now I can hook up, in order to model multiple masses like this, I can basically hook this guy up to the previous mass. Obviously, mass 2 represents q sub I plus 1. So I just take q sub I that comes out of mass 2 and I put it into q sub I plus 1. In my case, I'm going to just do, again, I'm going to set these up so that they look just like our problem that we did in class. So I'll set the limits on, I'll set the boundary conditions equal to 0. So now I end up with a problem that's a 2-mass system. 1, 2, spring in between it, a spring in between that and the wall, a spring in between that one and the wall. And I'll set, I don't need any F0s or whatever, any of those guys. But now what I should be able to do is let me see what the response is that I'll be looking for. So I'll take both of my outputs and put them into this scope here. So take Q2, Q1, press play, and now, oops. The ability to crash now. So awesome. So so the idea is now I've provided some displacement to these, to both these masses, and of course they both are vibrating in the first natural frequency. So now let me get rid of all the initial conditions, and I think the last step I asked for you guys to do before we get to the homework stuff is to excite this at some periods. So for example, I can put in a source that is a sine wave source, and I'm just going to put it in on this initial mass, right? I'm going to put it in as a forcing on this initial mass, and let's kind of watch what happens again. So like let's say for example, I'll grab it and I'll put it in my outputs. Okay, so now, if I take this initial mass and I put it in a frequency of 1 radian per second, then for our problem that we were looking at, again, let's recall, we have 2 natural frequencies that are associated with this system. Omega n1 is equal to the square root of k over m. which is the square root of, for our problem, 1 over 1, so that would be square root of 1 is equal to 1 radians per second. Our second natural frequency is equal to square root of 3k over m. Square root of 3 is, I don't remember the number, 1 point something, right? So the idea here is if I excite this system at 1.0, I should expect to see the first natural frequency. So what do I see here? So the blue line is my input. I'll simulate it for a couple more seconds than just that. Okay. So my blue line is the input, and the purple and yellow lines are the output. So let me see if I can do that bigger. Okay. So again, the blue line is the input. I'm just providing this little bit of input to it, amplitude of 1, whatever. And what's happening is, of course, I'm exciting this system at its natural frequency. What do you expect to have happen, right? It's going to blow, whoa, it's blowing away. There's no damping, there's no anything going on. You can see that I'm exciting it at its natural, or that it's following mode 1 because these two masses are aligned. Can you see that when one is up, the other one is up? They both have the same amplitude. So A1 for this time is 5 seconds. A2 for this time is 5 seconds. Right? So they're both at the mode ratio is 1 over 1, and they're both being excited. They're both following the same this same response. I'm pushing. Reorient ourselves. I'm pushing with some sine wave input on this one, and I'm getting both of them to respond in steady state. They both have the same characteristics there. All right. What would happen if I were to vibrate it at, let's say, a natural? I can't remember what the square root of 3 is. Let's just say this is the square root of 3. 1.7. All right. That's good to know. What would happen if I excited this thing at a frequency that was neither? Well, let's try 1.7. Just to square root of 3 here. If I have a frequency that I excited at the square root of 3, what do we expect to have happen? It'll also blow up, of course, because I'm exciting it at its natural frequency, but I can see that it's actually got a mode ratio that is +1 -1. So, it's hard to see, but at this time period here, right, one of them is high, one of them is low. Purple is high, yellow is low. Purple is high, yellow is low. Their mode ratios are equal but opposite. What, right? What happens if I excite it at some frequency that is neither the natural frequency nor the natural frequency 1 or 2? Let's just try 3. Natural frequency of 3. What do I get? You get some combination of mode 1 and mode 2, but the frequency, which is, I get some combination, I shouldn't say of the frequency. What I get out is, you can see, for example, that the mode, or that the frequency at which all of these masses are moving is only the frequency at which I input information. Okay, it's only. I'll do this one for. Let's do it a little bit shorter so we can maybe get a better view of what goes on there. Okay. So you can see that this one, if you think about what the frequency content here and the 0 crossing time and all this kind of stuff like that, this is equivalent to what the frequency is that I'm inputting. But obviously the amplitudes are some combination, there's not an easy to define mode ratio or something like that. These are the summations of the excitement that's happening at any particular frequency. Okay, so the idea here, and of course you can see that the displacement, the amplitudes, instead of going off into infinity or whatever they are low, right? In this case, 0.4 meters, 0.5 meters. Okay, so now the first question of the homework is calculate the natural frequencies of the system using MATLAB's eigenvalue function. So do the same thing we did in class, verify that everything works, etc., etc., etc. Construct a two-body mass system and allow it to have sinusoidal inputs, exactly like what we have already built right here, exactly what I built right here. Make this system, and then your objective is to excite it with sinusoidal inputs at a variety of omega. So I want omega to vary between 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, all the way up to 2. And what you'll do is just decide on some, it doesn't really matter too much, but decide on some time period that is the maximum, or that is the period that you're going to simulate it for, and plot out on semi-log axes the maximum displacement of mass 2 is a function of frequency. So what I want is a plot that looks like this. Here's the semi-log axes or whatever, okay? Yeah, I want it semi-log so that I can show log very. This should be log, sorry. And then this will just be frequency input. And what you'll find is at very low frequencies, we can try it. Let's just try it together for a sec here. I'll try a frequency of, the first one was 0.1. And let's just choose some number that it doesn't really matter what it is, 100 seconds or something like that. I'll simulate it, and I'm going to watch and look at what the maximum displacement of mass 2 is. The maximum displacement of mass 2 on this one is, I don't know why I did this to me, but I don't know, 0.5. So I'm just going to plot here at 0.1. I'm going to plot 0.5. A2 is equal to 0.5. That's one, of my plots. Then do it again, then do it again. And what you'll find is, of course, that we get at the natural frequencies, we get these explosions in amplitude, right? We just looked at it before. If I do this same problem at the natural sine wave, amplitude bias. What the hell happened? I keep getting into like discrete mode. How does that happen? No idea. Okay. If I do this at 1 frequency radian per second, then of course I get this giant amplitude. In this case, the maximum would be 25. And then on the other side, of course, it'll pull down. Then you'll have a couple of points down here. So this is at omega n1. At omega n2, you'll have another point, and it will look kind of like this in time, right? So these are things we know, right? That if you excite a system at its natural frequency, you'll get this explosion in amplitude. But then if you excite it at other frequencies, there's some amplitude, but doesn't go off the cliff. So you guys should be able to plot this. Maybe try it do it at 10. But if you can come up, it's really easy. In fact, in MATLAB to come up with something that will automate this. So that way you don't have to be taking 100 data points or something like that. But come up with a little, you can come up with a little script or something that will run the simulated program and record the maximum and save yourself some time. It doesn't have to be accurate to 10 decimal points or something like that, but just at least so you guys can see what that graph looks like. Does that seem doable? It's basically running this code 10 times. Now, last thing is plot the natural frequencies and mode ratios of a 10 mass system, just like we did in class. Explain what's going on, tell me what's happening, make a nice legend, make a nice figure that can help me understand that you understand what's going on. And then the last thing here is the tricky part, okay, which is what we talked about. All the things that we've done in this case have been to model systems that have equal springs, equal masses. The M1 is equal to M2 is equal to M3, and K1 is equal to K2 is equal to K3, right? And so what we end up with in those cases is beautiful mass matrices, for example, that have values for our 10 by 10, right? It would have 1, 0, 0, 0, 0, 0. 1, 0, you know. 0, 0, 1, 0, 0. 0, 0, 0, 1, 0. 0, 0, 0, 0, 1. Right? This would be a five mass system with this beautiful mass matrix. Its K, the stiffness matrix in this one is going to be 2K minus K, 0, 0, 0. Minus K, 2K minus K, 0, 0. 0 minus K, 2K minus K, 0, and 0, 0 minus K, 2K, whatever. Minus K, 0, 0, 0, minus K, 2K, whatever. The point is, we end up with, again, well-defined, beautiful, symmetric spring stiffness matrices. Now, in this case, what I want to do is I talked about it, we talked about this a little bit in class, so hopefully we'll go quick here. But the idea is that let's say we had some blades, and these blades have two springinesses associated with them. One is a springiness that joins the blade to the root, and one is that there's sort of a springiness that connects, a spring that connects the one mass to another mass. I plus 1, I minus 1. So this one has a displacement that's associated with it that is q sub I minus 1. This one has a displacement that is q sub I. This one has a displacement associated with it that is q sub I plus 1. So in this case, we basically end up with the exact same problem set that I described before. Like this part of the equation looks the same, right? Where I have some partial derivative, d q sub I dt squared. So the second derivative of the first displacement of x sub I or whatever is acted on by the springs that join it to its adjacent neighbors. So this part of the model looks exactly like what we've done on the board, right? The second part of the model that I want to describe is that there's also a springiness that is associated with q sub I itself, of course. Like if this blade, regardless of what's happening anywhere else, moves, then there's a returning force that comes from the blade root, of course, right? If I bunged it, this would go and vibrate like this, even if the air movement is turned on. So our challenge on this one is to write up the stiffness and mass matrix that is associated with this 10 by 10 system, to code it into MATLAB and run MATLAB's eigenvalue function to see what the answer comes up as. If you do it with, with all of these k, so I have two k's here, one is k sub air, and one is the k of the base or something like that, k sub b. If you make those all equal, what we'll end up with is some beautiful thing that looks just like our strings, right? It'll have a first mode that will be, oh, everything is moving together and doing this kind of stuff like that. You'll end up with a natural frequency that I don't know what it is, but it's 100 hertz or something. Okay, that's great. If you include, and that's what I asked you to do here, is a df sub I, which is a sort of a wear factor. And what we're going to do is we're going to take that base stiffness and increase it or decrease it by 10%. So that some blades are going to be strong, some blades are going to be weak, some blades are going to be worn, some blades are going to be unworn. What we'll end up with is this idea of mode localization. And so there's two dangers of mode localization. First of all, it's that what I talked about, that what happens is instead of having a beautiful string-like, sort of first mode, which would be the mode at which a gas turbine would vibrate as you move through its resonance, you'll end up with a first mode that looks like this. Bing, well, whoever the weakest guy is, whoever the weakest blade is, he takes all the energy, takes all the displacement. His displacement is 10x what the first mode is. He starts banging into the blades next to him and everything goes down. Okay? Also, you'll find that this natural frequency will, in general, be lower than the natural frequency at which you expect to find resonance. That's dangerous from the point of view of design, right? That you sort of say, oh, you never know, I promise you, buddy, boss man, we're way under natural frequency, like, it's not going to be a big deal. Well, if you get a little bit of a weak part, then you end up being at natural frequency and in a destructive way. So let's try, in the 1 minute we have left, to write up the mass and spring equation for this system. Okay?
Blades.
For the blades. Because that's the hard part of this homework, hopefully. Hopefully putting it in I it should be easy, right? But the mass matrix for a 10 by 10 is just going to be equal to M1, 0, 0, 0, dot, 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 M2, dot, 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 M3, dot, 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 dot. In this case, I give you a, I've sort of normalized everything so the mass is always just going to be 1. So you could just have a mass matrix. It's very easy to construct. It's I, right? I sub 10, or whatever you want to call it. It's just the identity matrix, right? What about the spring? The stiffness matrix. Let's just go through it, right? Okay, so let's talk about for blade number 1. For blade number 1, there is a stiffness that is associated with Q sub I. So the first value is going to be K sub B times 1 minus, dF, or whatever that is, I think I call it, yeah. And then there's a stiffness that is associated with the air, so that's plus 2K air, or whatever. That's the first term. Then Q sub I plus 1 is going to have a stiffness associated with it, so this is going to be K air. And I think I got the sign. Yeah, so this one's okay. That one has to be a negative sign. And then this goes 0, 0, 0, all the way out to 10, right? Except for that because we're going to treat this blade as if it's a circle, so if this is Q, or if this is like, for example, body 1, we'll call it Q1, then on one side of it is body 2, and on the other side of it is, of course, body 10, right? So what I have to do is I have to put one term that is, I'll try to draw square brackets around it or something like that, that's associated with Q1. This term is associated with Q2. Then I'm going to put 7 zeros, 1, 2, 3, 4, 5, 6, 7, until I get to number 10. And this one will have a minus K air. And then I can close out that row. So I have 1, 2, 9, 10 entries. Right? So the idea is that what's happening is that it's just like as if we had our masses and springs. They're all joined to each other with spring, except for the matrix just has to wrap around, right? So I'll go to the next one. The next row should read minus K air, then K blade, 1 minus dF, plus 2K air, then minus K air, then 7 zeros, 1, 2, 3, 4, 5, 6, 7. That's even that row. What's the next one read?
0.
It's pattern, right? What's the last one read? 7 zeros, 1, 2, 3, 4, 5, 6, 7, and then actually I don't need to say it should be minus K air, 7 zeros, then K blade, 1 minus dF, plus 2K air, minus K air. So see how that works? So all I've done is I've taken our line of masses and I've wrapped them around. So now instead of having a pure triangular or tri-diagonal matrix or whatever, I have a tri-diagonal matrix with some other stuff going on. And what that does, it just connects mass 10 to mass 1. So in this case now, I want you to compare the mode shapes for perfect and for worn. So set delta, set del F or whatever equal to 0, 0, 0, 0, 0, 0 for one of them. And for another one, just do a uniform distribution so that you can get a del F. You can do that with the MATLAB RAND function or whatever, but that's kind of the idea. And so then the idea is, right, describe what's going to happen, tell me which one has the lower natural frequency. So the danger is here that if you design some system that has, where you say, oh, that was no big deal, I did all the eigenvector problems, and it's like, I know just what's going to happen. I know what frequency my shaft is going to rotate at because I modeled all of the different components in my shaft. Well, if you're counting on all those components being sort of having some characteristics, the smart thing to do is vary those characteristics plus minus 10% or something like that to make sure that you don't get mode localization, that you don't get a component that's gonna fail at what you'll see. It will be a fraction of your model perfect natural frequency. So we're going to live in a we're going to do this model, and we're going to live in a world of imperfect system dynamics, and you'll find that it has real ramifications for if you're trying to think about failure modes of gas turbines or of any of these vibrating systems, right? Does that seem doable? Does that sound like you got the roadmap for it? Okay. Let's. That's that. But I think I have a couple of minutes to answer questions too if you guys have Instagram.
Yeah, I was like,
no, I think for the first one, he was just saying like, so you can compare it, like if they're all perfect, they would all be 0, and then the other one, it would be like each one is different x.
I apologize. I meant you all fix this one in Q, but the idea is it really just represents the generalized. So it can be, part of the temptation is the way we construct these things that are modal analysis or whatever. Again, it would be true if this Q was a position. It would be true if this was a charge in an electrical circuit. It would be true if it was a flow in a hydraulic. It's all, the idea is that it's supposed to be general, more general. Because right here, that's what I'm doing. I'm sort of making a really, in this case, a kind of a sloppy comparison between the vibrational springiness of this in the rotational domain and also the translation. So is Q a translation or a rotation? But who cares? I mean, I can make it. I can make it springiness associated with the translation. Rotation. It's inconsequential. Yeah. So I mean, it's a good question. Oh, the only other thing I was going to say too, I hint at it right here. I apologize I didn't say it explicitly, but I want you guys to model the air spring constant as something like a 400th or whatever base spring constant. Right? So the air is much less stiff than titanium. So just use that as your K there. You can use a K of the base that is 1, just whatever the ratios are you guys choose. Just make sure you don't set both equal to each other or else it'll be very easy.